All right, guys. So let's look at this example over here. So in the circuit below, the battery EMF is 50 volts. The resistance is 25 ohms, and the capacitance is 0.5 microfarad. The switch S is closed for a long time interval, and zero potential difference is measured across the capacitor. After the switch is open, the potential difference across the capacitor reaches a maximum value of 150 volts. What is the value of the inductance? Now let's start, trying to understand what's going on before we open the switch, because we are told that the switch S has been closed for a very long time interval, and then the zero potential difference is measured across the capacitor. Well, think like this: if you close the switch, then what you have here is you have a resistor connected to the inductor and capacitor where they're parallel to one another. The idea here is if it's been closed for a very long time, then the capacitor is fully charged. When the capacitor is fully charged, there is no current through the capacitor. Okay, that's why it says potential difference across the capacitor is zero. That means there is no current going here. Current through the capacitor equals zero. But there is a current here, and because it's been open for it's been closed for a very long time, that means inductor also doesn't oppose the current because it's already reached its maximum value. So this inductor basically acts like a wire. So what we have is that a resistor connected to the battery, pretty much like that. So I can just completely ignore this, completely ignore the coil that just pretty much acts like a wire, and assume that the maximum current is just equals to then EMF over the resistance. Okay. Now, this basically before we open the switch. Now, when we open the switch, what happens here is once we open the switch, then battery and resistor basically just removed from the circuit, and we only looking at then this part of the circuit because everything else is basically disconnected from it. And what we have here is as soon as we do that, when the switch is open, again, we can assume that the battery and the resistor, the current through them no longer, there's no longer any current through them. And the only thing we have here is basically the current, provided by the charged capacitor. That means now there's going to be a current in the circuit due to that. But then this is basically become just a RLC circuit where the potential energy, electric potential energy stored in the capacitor plates in the electric field, then can be converted into then magnetic field, magnetic energy in the magnetic fields, and back and forth. That means in a way we can interpret this problem as the voltage amplitude of this oscillations, right? So delta V basically can be represented in terms of 1/2 C times delta V squared, which is basically another way of writing electric potential energy in the capacitor, is then going to be equals to then 1/2 L I square, which is then the current, the magnetic energy in the inductor. That means we're saying that the maximum amount of energy is basically for both of them pretty much is exactly the same. So how much you can calculate for the maximum amount of electric potential energy, you can assume the exactly same amount is for the magnetic, potential energy. Then using this equation, we can assume that if we cancel the 1/2, so we have C times EMF. So this potential is just basically your EMF because it's an ideal battery. So C times EMF squared is equals to Li, this is I max basically squared. Okay. Then from here we can just rearrange and solve for L. And L will be equals to all right, sorry. So EMF and delta V are not the same because we're given EMF as 50 volts, but delta V is actually, remember, so capacitor reaches maximum value of 150 volts. So that means that's basically a difference. So then this is pretty much, let's write this as like delta V squared. So Um, L is equals to then basically C times delta V squared divided by I max. But this is same as I max is over there, which means that I can write I max as, sorry, it's I max squared, as the EMF of the battery divided by the resistor. That means I can write this as C times delta V squared divided by EMF squared divided by resistance squared, or EMF over the resistance, the quantity squared. So then this becomes C times delta V squared times resistance squared and divided by EMF of the battery squared. And then we can plug in all the values, right? So the capacitance is given as 0.5 microfarad. So 0.5 times 10 to the negative 6. Delta V is 150 volts square. Resistance is 250 ohms square. There you go. And then divided by the 50 volts squared. So we can calculate the inductance to be 0.281 Henry, or we can just write this 281 millihenry. So the Henry, or um, the value of inductance generally is in micro, or a milli, right? So that means, remember, so in terms of, like, let's say the value of Henry is approximately maybe from micro Henry to maybe a few Henries. You're never going to get like thousands of Henries or hundreds of Henries. That's a humongous amount for the inductance. That means you should be approximately verifying your work by looking at the value that you got. That means millihenry, microhenry is something that you should expect. Even nanohenry, it's a very small amount of inductance, and maybe like hundreds of henries is a huge amount of inductance. So that's kind of like the range of from microhenry to maybe a few henries. All right. So now next, let's look at RLC circuits. So for RLC circuits, then what we have here is R is the resistance, L is the inductance, C is the capacitance. That means we have all those three things together in a circuit. So we can think of it like in terms of getting the equation and everything for the RLC circuit. Let's use the circuit over here in the diagram. We first start by, in a way, it's exactly the same thing that I had for the LC circuit, but now I added extra resistor here. So, but still, the switch right now is thrown at position A, which means what we have here is this part of the circuit is pretty much disconnected. That means, it's just not part of the circuit at all. Okay. So let's assume that right now we have the EMF connected to the capacitor, and the switch is thrown to position A, and let's assume it's been there for a long time. Okay. Which means that the capacitor has been fully charged, and it has Q max as the maximum charge, and then the current here is basically equals to 0, right? That there is no current because the capacitor is fully charged. All right, so now, assuming that at this point we're gonna, take the circuit to be more or less ideal circuit, in a way that there are no such thing as, so like electromagnetic radiation from a circuit or something like that. We can assume that there's always going to be some kind of conservation of energy when I take the switch and throw from position A to position B. By doing so, I completely disconnect the EMF source. That means the battery is completely taken away from the circuit. And then what I have here is I have now capacitor, inductor, and resistor in series together, right? And the battery, since it's now disconnected, the capacitor is going to act like the source of energy, because at this point all the energy in the circuit is stored in the electric fields of the capacitor. Okay, that means we can again assume that there is a conservation of energy if we take into account that we can take the energy that dissipated by the resistor to be represented by the internal energy. That means we can say that change in electric potential energy plus change in magnetic potential energy plus changing then internal energy, which is, changing internal energy is basically the energy dissipated by the resistor. So then we can say that this is equals to 0. That means the sum of changing potential energies will then give us 0. All right. Now, if I then calculate then the rate at which their energy is changing, so due dt plus d dt of the ub plus d dt of E internal, and then set this to 0. Okay, now we already worked with this one, at least for this 2 here in a few slides ago. So this is basically q over c dq dt plus li di dt, then plus, and this is basically the energy dissipated by the resistor. So we know that dE dt is nothing but the power, right? Power is just dE internal dt. And then we know that power, dissipated, which is the energy per unit time dissipated by a resistor, can be easily represented by current squared times the resistance. That means I can write this as current squared times the resistance, and this is equals to 0. All right. So now what I can do from here is just, rearrange a little bit. So then Q over C is, well, dQ dt is just I, then plus Li, then I have di dt, then plus I square R equals 0. Now, for example, the right side of the equation is equals to 0. So let's take and get rid of the, one of the i's. That means we can just divide both sides by I. So then this cannot cancel out. Then what I end up with is, in terms of L di dt plus R. So I have then over there I, which can be, let's first write it as I, then plus, then Q over C, which you can see, right? It's a derivative of the current, then the current, and then the constant, then this equals to 0. But what I want to do here is I want to look at the equation for the charge, because I can always take the equation for the charge and take the derivative of that and get the current. That means I'm going to replace di dt with d squared q dt square, okay, and I with dq dt. So rearranging this, so L d squared q dt square plus R times dq dt, then plus q, or you can think like, let's say it's 1 over c times q equals 0. Okay, now the reason we're doing this is so that we can recognize this equation, or at least the format. So this is, it's a differential equation, right? So one of the things we have is just basically for us is to recognize the solution for that. Okay, now the solution for this is relatively complicated, and most of the time what we do, we try to find something that is already we already know the solution of. So for example, if I have m d square x dt square plus b dx or dt plus kx equals 0. Now, this equation is for the dumb simple harmonic motion. And we have, studied this before in when we looked at waves. So you would have studied this in the previous class. And what we do here is we recognize that this format basically gives us type of equation, right, for the, let's say for the x, that was in terms of, x max, x is equal to then x max, then e to the negative t over tau, for example, that was the solution for this, right? Then you have cosine omega t, let's say plus phi or something like that. So this was the solution for that. That means we can do the similar thing here by recognizing that our equation is basically same format. Some constant times second order derivative of the q, then some constant times the first order derivative of the q, then plus let's say the q itself, which is basically same as that second order derivative of x plus first order derivative of x, and then plus x. And that, we got the solution for that like this. So using that, we can then write down the equation for Q. So Q is equals to maximum charge that we started with, then e to the negative, then what we have here is this will be RT divided by 2L. That's the, the exponent for the E. And then we have then cosine omega D times T. Okay. Now, where the omega D here is then the angular frequency at which the circuit oscillates. So remember, omega D here is the angular frequency. And one of the things we can do here is the tau is, remember, it's known as the time constant, right? So, and we have then R and L, which basically will be in terms of, like, let's say tau is equals to L over R. So then it's T over the 2 tau. That's the equation for the Q max. Okay. Then we can say that this is the solution for that differential equation. Okay. Now, one thing we have here is then omega D is equals to, since this is not the same angular frequency that we had for the LC circuit, because now there is a dissipative component, right, to that. So this is equals to then square root of 1 over LC, then minus R over 2L squared. And this is all inside the square root. Okay. That means what we get here is we get equation for the RLC circuit, right? So this is basically for RLC circuit, where what we have here is, if you remove R from the circuit, let's say just L and C, we notice that the circuit basically just conserves the energy altogether, but it's just a magnetic and electric energies. It goes back and forth, back and forth, back and forth. But here what we have is that now the magnetic energy and electric energy are going to decrease as a function of time, and they're going to be slowly converting into basically internal energy. And then the Q max, which before was able to always come back to its original value, right? So basically you had a Q max that would go to like 0 and then go to negative Q max, because the capacitor would change the polarity, right? But it always would come back and oscillate back and forth between its Q max, plus Q max, and negative Q max. Same with the current. Now that's not going to be true anymore, because the resistor will be pretty much dissipating, right? Just basically dumping that those oscillations. Okay, that means now we have the equation, and in a way, like, let's say we can also look at it in terms of the current here equation by taking the derivative of this one. Okay. Now, in terms of, you can write I is going to be like, let's say dq dt. So you can also look at it in terms of that. Current also, undergoes damped harmonic oscillations. Okay. We are ready to kind of summarize everything here. You can write analogy between RLC circuit and the particle in damped harmonic motion. And if you don't remember how exactly the damped harmonic motion works, I recommend you guys review, because it's much easier to understand damped harmonic motion and then use that analogy to understand RLC circuits. So here what we're doing here is the X is the the position, remember. So this was basically, you have a spring with the mass attached to that. So you stretch this to some position X relative to its equilibrium, and then you let go. Okay, if there is no spring, if there is no friction, the system will oscillate back and forth relative to this X equals plus A to X equals, let's say X equals negative A positions. So it's going to oscillate back and forth forever if there is no friction. And that would have been sort of like very similar, as we looked at, right? Very similar to the LC circuit. LC is just basically like a simple harmonic motion, right? Without, dumps. It's not the damped harmonic motion means that now you have a friction. That means simple harmonic motion is a frictionless surface. So the black goes back and forth. Same thing we have here, for the LC circuit. But RLC is then, imagine that the surface here now basically rough. So then instead of simple harmonic motion where the system oscillates like this, so with a damped harmonic motion, it kind of slows down, eventually stops, right? So that means every time then it goes back and forth, it's going to reach less distance until eventually, stops at an equilibrium. Okay. That means for us, Q is same as X. That means the same thing with the charge, right? Q max, you start with when we, remember, so we started with this, right? When we throw this at B, you have Q max at T equals 0, right? You have Q max. But as a function of time, this Q max basically decreases because of the resistor. Because of the resistor, you never can recover the same amount of charge again. So it still oscillates a little bit, but it will never come back to the same maximum value. So that's why what we have here is that, x, q is similar to x, I is similar to the velocity, because velocity is the time rate of position and the current is the time rate of q. Then potential difference is sort of like, analogous to force, which because it's a driving, mechanism, right? What drives the current? Delta V. What drives the particle? Well, the force. So, and in the damped harmonic motion, we had then this viscous damping coefficient, right? B, and then for us, it's just basically the resistance R. Okay. So the capacitance is analogous to 1 over K, and then inductance is sort of like analogous to mass. Okay. And then you can see, right? So all of this is then just basically pretty much what we kind of talked about. So the I, which is the dq dt, is equivalent to the velocity, which is dx dt. Then you can say, right, di dt is d squared q dt squared, where then acceleration is basically d squared x dt squared. And then we have the kinetic energy, which is, analogous to the magnetic energy, and potential energy, spring potential energy, which is analogous to electric potential energy. And then this is the equation for the damped, particle and damped harmonic motion. This is the equation for the RLC circuit, where inductor, resistor, and the capacitor are connected in series with one another. Okay. So here you can see sort of like, let's say, what happens with the Q max, right? So this is basically the plot of charge versus time for a damped oscillator. So the oscillator, you can see, right? So this is, actually, the picture from the oscilloscope. So you can see that you're starting from Q max at T equals 0. But what you get here is, you can see, right, when it oscillates back, you no longer have the Q max. That means every time is less and less and less and less until eventually, you have a completely discharged capacitor. Okay. Because all the energy then, magnetic and electric energy, eventually converted to internal energy. Basically heat, right? Heat internal energy by the resistor. Now, in terms of then what we have here is how long it will take for this to basically the damped out. It depends on the value of R. So you have for when the resistance is very small, then in a way you can predict that, let's say, some of the values can be very similar to the non-damped, let's say, example. So let's say when we looked at just RLC, that means you have sort of like, let's say this, right? R is much less than, so kind of like write it down. So this omega d, which was equal to square root of 1 over LC minus R over, basically it's R square over, 4L square, right? So pretty much this. Now, when R is much less than square root of 4L over C, okay. So this is, you can say that this basically makes this, this part is nearly 0, and omega d is, pretty much as 1 over square root of LC. Okay. That means frequency for damped oscillator is close to that of undamped oscillator. Okay. And this is, in a way you can think of, like, let's say it's a very small resistance. So you can approximate this to be basically almost same as if there was no resistor. But then what we can have here, we can have a resistor where, like, let's say at some larger values of R, right, oscillation dump out more rapidly. So then higher the value of resistance, more rapidly it will dump out. And then at some point you reach what we call critical resistance. Okay, critical resistance, where here's the value of that critical resistance, where RC is equals to square root of 4L over C. Then at this point, when R is equals to RC, then you get critically damped. Okay, and then when we have basically critically damped, you can think of, like, let's say, this critical resistance value, right? In a way makes it like, so let's say there's almost no oscillations occur. And then what you get here is that when R is greater than R over C, that means any R greater than the critical resistance, then you get overdamped. Okay, that means you can see, right, larger the resistance value, much quicker your systems basically just, the energy or all the other type of energies converted into basically the internal energy of the system. All right, so the last kind of like the real life application here we have is basically in terms of looking at why sometimes when you approach an intersection, especially at night, the traffic light suddenly changes to green, even though it was red. But as soon as you approach, it kind of changes to green. That's because those circles that you see over there, those represent basically coils under the road. Okay, so the circles basically are the wires, right? The loop of wires buried under the street surface. And when your car approaches, that's basically a moving conductor, right? So when the car approaches, the metal of the car represents a magnetic material, and that alters the magnetic field passing through the loop. Then what we get those eddy currents, which then are induced in the metal of the car, producing additional magnetic field lines. That means, the moving conductor, we learned especially in the motional EMF, moving conductor can induce, current and EMF in those coils that are under the street. Okay. So then the change in inductance L of the loop then changes its natural frequency of oscillations. Then the control electronics basically that are connected to those coils detect the change, and the signal sent to the traffic light, which then changes from red to green. Okay, that means, every time now you approach a traffic light, especially at night, as I mentioned, right? So when the traffic light right away changes to green, hopefully now you understand why, and maybe you can even look at and see those coils. So that means there's a coil under the street, and you are, when you're driving your car, it induces EMF and current in those coils, which then basically sets up the chain reaction, which eventually signals to the traffic light that there's an approaching car, and it changes to green. All right, guys, that's it for this chapter.